So welcome to our fifth lecture dealing with transition metal chemistry, that is coordination chemistry. To finish off our discussion of isomers, so far we have been looking at octahedral complexes. And for the metals in the middle of the transition series, like cobalt and iron, we do in fact see overwhelmingly they form octahedrons, that is, they are 6-coordinate. But what about the metals that are at the end of the transition series? Things like copper 1 and silver 1 and zinc 2 plus 2 ions. They don't have to have 6 ligands around them. They already still have 10 valence electrons. And so get the next noble gas count doesn't require 12 electrons, it only requires 8 electrons. And so they're not going to be interested in picking up 6 ligands. They're only going to be interested in picking up 4 ligands. And so we do in fact see coordination numbers of 4. Between them, 4 and 6 account for most coordination spheres, although some of the other metals have other ones possible. For 4-coordinate, we have 2 possibilities. We can have simple tetrahedral coordination, or we can have square planar coordination. The tetrahedral complex basically doesn't form any geometric isomers. There simply isn't enough variety to it. The one exception being, of course, is if you had 4 completely different ligands on it, you would end up in the same case as you see in organic chemistry, where a carbon atom has 4 different things around it, in which case you get optical isomers. The square planar arrangement does in fact permit geometric isomers. When you have 2 different ligands on the central metal, you again have a possibility of cis-trans, whether the 2 ligands that are the same are beside each other or across each other from the square. And so again, we don't have a whole lot of possibilities for isomers. If I were to show you 100 bottles of aqueous solutions that contain ionic compounds, you could probably tell me which ones contained cations from the main group elements and which ones had transition metals as their ions. And you would probably be right 90% of the time. And why is that? Why should you be able to tell simply by looking at a solution whether it has transition metal ions in it or not? And the answer, of course, is because the solutions that contain cations from the main group metals would all be virtually colorless. Overwhelmingly, the main group metal cations in solution form colorless solutions. On the other hand, the overwhelming majority of transition metal cations in solution form colored solutions. And so just by looking at solutions and picking out which ones were colored and which ones weren't colored, you would be right about which ions were present 90% of the time or more. And so that becomes a question. Why do compounds of the transition metals end up giving colored solutions? Well, to approach this, we're going to use what is known as crystal field theory. When they were first doing X-ray crystal structures, they were trying to account for what was going on in this lattice. And so they developed an idea of what happens when the ions come together. We've already considered what would happen, for example, in a simple sodium chloride structure as the ions come together. The sodium ion would be in the center. The 6 chlorines would be approaching down the axes towards it. Until now, we've treated the ions as if they were just hard spheres with charge on them. And that, in fact, that simple approximation actually gave us fairly good results. We got lattice energies and densities with an error of about 10%, which is pretty good making that simple assumption. On the other hand, the reality is the ions are not hard spheres. they are in fact atoms or cations. They're a nucleus surrounded by a swarm of electrons, and the electrons are moving. That is the electron cloud. And so as the charges come together, those charges begin to interact not with other just hard spheres, but with the electron clouds. And so what effect does having the ions come together have on the electron clouds of our central metal ion? Well, the effect of the anions on the electrons in an s orbital is fairly simple and straightforward. The electrons in the s orbital don't like it. That is, they don't like the approach of the negative charge. And so the energy of any electrons in an s orbital in this crystal would be shoved up by the approach of the anions. In the same way, the p orbitals all point straight down the axes. And so again, as the anions approach, they are interacting directly with the electrons in those orbitals. And again, that would have the effect of shoving the energy of all the p orbitals up, because they did not like the interaction. The case, however, is different for the d orbitals. If you go back and remember the shapes of the d orbitals, they provide a different case than the s or the p's. 3 of the d orbitals have 4 lobes. The dxy, the dyz, and the dxz orbitals have 4 lobes. They're each in their respective planes, but they're actually in the quadrants. That is, they are in between the axes. And in fact, those orbitals don't have any presence actually on the axes. We talk about nodes. There's an area of 0 density for those orbitals along the axes. So the ions, as they come in the axes, are actually missing those orbitals completely because they're coming down the nodes. That leaves the other 2 d orbitals. The dx squared minus y squared orbitals has the same shape as the dxy does, but unlike the other orbitals, the other 3 orbitals, it is in fact oriented straight down the xy axes. And so the ligands, or rather the ions coming down those axes, will in fact run directly into those orbitals, shoving them up in energy, because we said the electrons don't like the presence of the anions. Which brings us to the weird-shaped one, the dz squared orbital. The dz squared orbital, of course, has 2 major loops along the z-axis and a sort of ring in the xy plane. And again, those are all going to be directly affected by the anions as they come down the axes towards the metal center. And so that orbital will be shoved up in energy. And so we have an effect. The presence of the anions splits the d orbitals. 3 of the orbitals, d orbitals, end up lower in energy, and 2 of the d orbitals end up getting pushed higher in energy. We've created an energy gap within the d orbitals, which previously, of course, were degenerate. That means they had exactly the same energy. Now the d orbitals have different energies. And that's important, because it means if you move an electron from one of the d orbitals to the other d orbital, you are in fact changing the energy of the electron. That is, it has to come up with energy to either be absorbed or emitted as it moves up or down across this energy gap. And it turns out that the energy to make this transition up or down has a frequency that corresponds to visible light. In other words, moving an electron from one of these d orbitals to the other is going to either emit or absorb visible light. And so we see one of the major differences between the main group metals and the transition metals. For the main group metals, they don't have any d electrons, or their d electrons are full. That is, they're either d0 or d10s. And as a consequence, it doesn't matter that the d orbitals are split, because there either aren't any electrons to move across the gap, or the orbitals are already full, and so it's not possible to move electrons across the gap. And so they don't respond to having these d orbitals split. The transition metals, on the other hand, the d orbitals are partially full. There are not only a gap, but there's places for the electrons to move through. And so we see the transition metals have something in this gap to move and therefore be colored. The obvious exceptions, of course, are the transition metals at the end. A scandium plus 3 is also going to be colorless because, of course, it also doesn't have any d electrons, whereas a zinc plus 2 is also going to tend to be colorless because it again has a D10 configuration. But the transition metals that are in between, that both will have an energy gap and have some electrons in those d orbitals, they'll be able to respond to this energy gap and have the electrons move from orbital to orbital and change energy and therefore be colored. So we expect the transition metals to give us colored compounds. But that's in the crystal. What about in solution? In this case, we have to generalize the idea, and we get what is known as Ligand Field Theory. In Ligand Field Theory, we generalize the idea of crystal field theory that the anions are providing negative charge, which is causing the split in the electron orbitals. Well, of course, providing electron charge is just exactly what the ligands are doing in a coordination compound. And so the effect of the ligands is the same as the anions in the crystal structure. They're pumping electron density into the orbitals of the metal at the center, and as a result creating a split. The interesting thing is unlike a crystal, where the size basically is stuck depending on the size of the ions, the ligands, in fact, have some flexibility. They can either come in close or stay far away. They can either be really good donators or really lousy donators. And so we see that the energy gap depends on how strongly the ligand does in fact interact with the metal center. The more strongly the ligand interacts, the bigger that gap's going to be. The more weakly it interacts, the smaller the gap's going to be. And of course, it is the moving across the gap that the electron is doing in absorbing or emitting energy. And as the gap gets bigger, therefore, it's going to need more or less energy to make that gap. So in other words, we're going to get different colors from the interaction of the ligand. And so we get what is known as the spectrochemical series, where the best ligands produce the biggest gaps and the worst ligands produce the smallest gaps. And we see a nice whole long sequence, which is fairly self-consistent. And basically what we see from this group is the halogens tend to make lousy ligands. That's not entirely surprising because, of course, the halogens would simply be spherical since they have noble gas shells, and so they're not really good. They don't have any really accessible lone pairs, and so they're not that good at it. Next, we see oxygen. Compounds that are coordinating through the oxygen tend to be also not especially good ligands. Then we get to nitrogen. The nitrogen's ligands tend to be very strong that are using the lone pair on the nitrogen. And finally, we get to the best, strongest case where the lone pair is on the carbon, as it is in cyanide or carbon monoxide, and those tend to produce really big gaps, really strong interactions. And that brings us to the end of today's discussion on transition, that is, coordination chemistry. Have a nice day.